Okay, let's do the problems for chapter 11, torque and angular momentum. So in 78, we just take point A as the pivot. You can choose either one as the pivot, but I think it's a good idea normally to just take the first upward force on the left. So our force equation becomes FA plus FB, those are both upward forces, minus 36,000, which is the downward force, and that equals 0. And then our torque equation is, what we do is we do all the different torques. So remember that a counterclockwise torque is positive, clockwise torque is negative. And you always have to take into account where things would rotate if they could. So in rotational equilibrium, obviously things are not rotating, everything's standing still. But when you're looking at the pivot and you're looking at the force in consideration, you've got to figure out, okay, which way would it turn if it could? And that's going to determine the sign, whether it's positive or negative. So then what we have is a system of two equations. The second equation has only one unknown, so we can solve for FB. Once we find FB to be 14 kilonewtons, we just plug that back into the original force equation, and we get FA equals 22 kilonewtons. Okay, next problem is number 83. And so kind of a simple diagram here. We're just drawing Selma and Rocco as, little poles. If you wanted to make stick figures, that's fine too. But in any case, we have Selma, we have Rocco, we have the givens. We know that the weight, or we can figure out the weight, is 889.9632 newtons. We also know that the upward force is 533.8 newtons. That's the upward force of Selma's shoulder, right, going up, because what's on her shoulder is going down, so it's equal and opposite forces. We know the total distance between them is 1.829 meters, and x is what we would need to find. So we do our force and torque equations. Force equation, we got 533.8, which is going up, plus Fr, that's the force of Rocco's shoulder, that's going up, minus 889.9632 is the downward force, so that's got to add up to 0. Then the torque, what we're doing here, so we have negative 889.9632. Notice that if Selma is the pivot, then the type of rotation that FW wants to do at the distance x from Selma's shoulder is it wants to rotate clockwise. It can't, of course, but that's what it wants to do. And so we consider that a negative or clockwise torque. And then the next upward force, which is Fr, the way that wants to turn, if it could, is it would be counterclockwise, and that's why that's positive, and it's at a distance of 1.829 meters from the pivot. Then we just solve our system, and we find that Fr is 356 newtons, and x is 0.732 meters. So 0.732 meters away from Selma. Okay, move on to number 85. So notice that we've got the same type of thing again, force and torque equation. So FA plus FB, both upward, minus 9.81 times the two masses. Okay, because mg is mg is force. So 9.81 just distributes. Same thing as doing minus mg minus mg. Okay, so we just have our force equation, then we have our torque equation. 2.0 times 9.81 times 0.10, that's a counterclockwise torque, plus FB times 0.20, another counterclockwise torque, minus 1.0 times 9.81 times 0.40 clockwise torque. So we solve FB is 9.81 newtons, and the scale reading is mass for this particular scale. So that's going to be 1.0 kilograms. All right, 123. So this is what the force equation looks like, the force of the hands plus the force of the feet, because the hands and the feet are providing upward force, minus the downward force, which is the weight times 9.81. Well, sorry, the mass times 9.81. That's the weight. So the weight's going down. Now the torque equation, clockwise, negative 65 times 9.81 times 0.5, because the hands are the pivot. Plus FF times 1.50, that would be counterclockwise, because that's the way that upward force wants to rotate, if it could. So the force then is 212.55 newtons, and since they want to find what that is on each foot, it's going to be 0.11 kilonewtons on each foot. And then for the hands, what we do is we just put FF back into our force equation. And so we're able to find that FH is 425.1 newtons. So that's going to come out to 0.21 kilonewtons on each hand. All right, the next problem is number 135. And so just a simple sketch to start us off. The radius is the same as 13/12 of a foot. We know the torque is 50 foot-pounds. That's a given. And then we just convert feet to meters and pounds to newtons. So the conversion there is 0.3048 and 4.448, meaning that our given torque is 67.788 Newton meters. Now the force of weight, that's a given, 3.22 pounds. And so 3.22 times 4.448 means 14.32256 newtons, from which we can get the mass of the wheel, which is 1.46 kilograms. Now, since the moment of inertia of a hoop is mr squared, we plug in the mass we found, we plug in the radius, converted to meters, of course, and find that the I, or moment of inertia, is 0.1592 kilograms meters squared. Last step, tau equals I alpha. So then we plug in the torque we found and the I that we found, and this allows us to get alpha, which is the angular acceleration, 426 radians per second squared. Okay, moving on to 140. So this is the situation. We've got the pulley, and it's always good to lay out your torque and force equations. This helps you to visualize things and keep track of your givens and your unknowns. Okay, so in the sketch, we've labeled our givens and have also indicated the forces with vectors. Big M there, the mass of the pulley is 10 kilograms. We have the radius, we also have the mass that's falling. So the torque equation, net torque equals I alpha. Torque is the same as TR because T is tension. That is a force that acts perpendicular to the radius. And when a force is perpendicular to a radius, that's torque. It's force at a distance. That's where the TR comes from. The tension times the radius is the torque that makes this pulley turn. Now I is 1/2 mr squared because that's the moment of inertia of a disk. And alpha is the angular acceleration. This simplifies to T for tension equals 1/2 mr alpha. And since alpha, or since tangential acceleration is the same as r alpha, that is the radius times the angular acceleration, we can then replace r alpha with at. Okay, now let's look at the force equation. Net force equals mass times tangential acceleration. The weight is mg. The t, which is slowing it down, that's going to be minus, equals mat. So mg minus mat equals t, and m times g minus at equals big T. So now we put the two equations together. We get 1/2 mat equals mg minus at. All we've done is just use substitution because we know that big T is 1/2 mat. Then we plug in some givens, and we're able to find the tangential acceleration of 1.6 meters per second squared. Now, we also need to find the force and or the tension, and we know that that tension is 1/2 mat, and then plugging and chugging at that point, we get 8.2 newtons. Okay, the next problem is probably, I would say, the hardest of this particular problem set, because it's a situation you haven't dealt with before. In the past, we've always ignored friction or ignored moment of inertia for pulleys. And when you do that, of course, the tension is the same on each side. But when you take it into account, the tension is not the same on each side. All right, so what we've done is we've labeled one tension as T1 and another as T2. We've also labeled the radius. And we're given the frictional torque, which is 0.25 Newton meters. So first we need to write two force equations. We write two force equations because we have two masses that are traveling in straight lines. We only need one torque equation though, because we only have one rotating thing. So let's look at the first force equation. Net F1 equals M1 AT. Now for M1, we know that the heavier mass is going to fall down, the lighter mass is going to go up. That's why we do M1G minus T1, because we know M1G will be bigger than T1. And that equals M1 AT. Doing the same algebra leads us to M1G minus AT. That is same algebra as the last problem. So M1 parentheses G minus AT parentheses equals T1. We do a similar thing with the other net force equation. T2 minus M2G equals M2 AT. And that eventually simplifies to T2 equals M2 AT plus G. Now let's look at the torque equation. Okay, the torque equation is just net torque equals I alpha. So sigma tau equals I alpha. And we have T1R because T1 is a perpendicular force. And I can see here that T1 is perpendicular to this R. And so T1R is going to cause a clockwise rotation. But it's being slowed down. Now, normally we're going to consider clockwise as negative and counterclockwise as positive. But in this case, based on what they're asking us for, and we're trying to find a positive magnitude, we can switch that. If you didn't switch the signs, that would not be wrong on a test. I'm just explaining to you why we can switch them here. All right, so T1R would be a clockwise torque minus the frictional torque, because the frictional torque is trying to go the other way. It's minus because the frictional torque is opposing T1R. Now, T2R is this tension, same radius, but this tension is causing a torque that's in the opposite direction. It's not causing motion in the opposite direction. because the 10 kilogram mass overcomes the 5 kilogram mass. But it is slowing things down, and that's why we have a minus T2R here. And that, of course, equals I alpha. Okay, then we put everything together. And putting everything together is really just a bunch of algebra. So we have M1 times G minus AT R minus tau F minus M2 AT plus G R equals IAT over R. We do that because alpha is the same thing as AT over R. And then these arrows indicate that we've just simply replaced T2 and T1 with what we found for them earlier. Okay, then comes all the chugging. So all the plugging and the chugging, and that's a bit tedious. But if you proceed carefully, you find that AT equals 3 meters per second squared. Okay, number 147, conservation of energy problem. And for this one, it's really easiest to just keep things in symbols for as long as possible. There was something similar to this in the video for chapter 11. Okay, so we have our ramp and we have the mass at the top. We have the initial height. And we're asked to find the speed that it reaches at the bottom of the incline. So we set up our conservation of energy equation. PEGF plus KELF plus KERF equals PEGI plus KELI plus KERI. PEGF plus KELF plus KERF equals PEGI plus Kelly plus Kerry. Okay, then we just add, or we just kind of replace things with what we know. We know the final potential energy is going to be 0 because it's all converted to kinetic. And we also know that the initial kinetic energies are both 0 because it starts at rest. And then we fill in for KELF. We also fill in for KERF because we know there's rotational energy, and that's 1/2 I omega F squared, and then MGHI. Now, the remaining steps are just, again, a bunch of algebra done with symbols. And as you proceed, those symbols become simpler and simpler until you're left with VLF squared equals 4/3 GHI. So VLF equals square root 4/3 GHI, which is the same as 2 root GHI over 3 meters per second. All right, number 151, we want the rotational kinetic energy, so that's just 1/2 I omega squared. Pretty simple, straightforward problem, just plug and chug. So that omega is 4.47 radians per second. Okay, moving on to the last few problems of the set. Number 160. So we're given that the omega is 60 RPM. Now 60 revolutions per minute times the corresponding number of radians per minute gives us an angular velocity in minutes, and we can convert that easily to seconds. So we have 2 pi radians per second. Then, since angular momentum is I omega, we can just fill in the I for a disk, which is always 1/2 mr squared. And at that point, we can plug and chug to get 6.3 times 10 squared kilograms meters squared per second. 162, the linear velocity is r omega, so therefore omega equals the linear velocity over r. This is a synonym for tangential, so if you ever see VL or VT, it really means the same thing. Angular momentum is I omega. The I of a hoop is mr squared. The omega we just found, VL over r, and everything simplifies to 5.00 kilograms meters squared per second. And that brings us to the very last problem. Okay, so we have an omega I of 1/27th revolutions per day. We have an RI of 0.695 times 10 to the 9th meters. And we have an RF of 20,000 meters. So clearly the RF has decreased dramatically. Now, the final angular momentum equals the initial angular momentum. So LF equals LI, which means that IF omega F equals II omega I. II, Captain. And I of sphere is, the I of a sphere is 2/5 mr squared. It's from that chart that's in the lesson. So 2/5 mrf squared omega F equals 2/5 mri squared omega I. Notice that tons of things are going to cancel. So we're left with RF squared omega F equals RI squared omega I. And then we just plug and chug, and we find that the omega F is 4.5 times 10 to the 7th revolutions per day. So at this point, we just have to convert revolutions per day to radians per second. And so we do 4.5 times 10 to the 7th times 2 pi times 1 over 86,400, and we get 3.3 times 10 to the 3rd radians per second. Okay, hopefully that helped to see your answers, to see some of the steps. If you have any questions, of course, bring those to the review that we're doing Thursday. See you in class.